Well, hello everyone. I hope you are doing well on this fine Tuesday. Um, got about a week and a half left before Christmas break. I hope you have been catching up on your schoolwork and my class and other classes as well. And I hope you're having a good time and being safe. So, what we're going to start with today is I'm going to do the first half of the last section of Unit 2. Now, from what I've seen so far, Unit 2 has been received pretty well. Don't forget you had a quiz yesterday that's due tonight by 11:59. As of my recording of this video, there have been 22 people that have turned it in, so there are quite a few people left to go. So make sure you get that done. But I want to talk about today the first half of the last section. Now, of the three sections of this unit, this one is objectively the hardest. And that's because a lot of this is probably new to you. Chances are some of this stuff you've not heard of before, but we'll get through it and we'll do fine. So you need to have out your Unit 6 notes. I've been looking through those. I'm probably going to later in the day go and after I get my other stuff done, comment if you've not been filling it out. You need to be filling it out. Um, Most of Unit 6 so far has been fairly easy, but it's going to get a little bit more difficult in this one. So it's important that you pay attention and watch this video. This one's going to be an ed puzzle as well as the one for tomorrow. So you are going to have to watch it to get points for that. So I want to move over to 6.3, and once again, if it's in yellow, you need to write it down. Okay, so get that done. You'll be fine. You can do it. So 6.3 periodic trends. So you should fill out your notes while you are watching this ed puzzle. Okay. So the four learning objectives, or sorry, three, can't count. The three learning objectives you need to write for this section are first one is to describe trends among elements for atomic size. The second one is to explain how ions form. And the third one is to describe trends for first ionization energy, ionic size, and electronegativity. So today we're going to talk about the first two. And then the last one is what we will do tomorrow. So we're going to talk about atomic size today, which is the atomic radius, what trend it has going left to right and up to, top to bottom on the periodic table, and we're going to explain why it happens that way. And I'll give you some examples related to that. And we're going to talk about ions for the first time this year and explain how they form, because ions are very important for the rest of the school year, as you will see for sure. So, put some memes here that you can watch. I'm going to play this video of Kevin from The Office.
Me mechanic not speak English, but he know what me mean when me say car no go, and we best friend. So me think why waste time, say lot work when few work do trick.
I feel like the best advice you can get is usually from Kevin. All right, so we're going to start with trends in atomic size. So what are the trends among the elements for atomic size? And that means atomic radius. So let's talk about that. So nothing on this slide that you need to write, but you do need to listen. So right here, this isn't the best representation of this because I have a little bond in between them. But as you see right here, we'll say this is hydrogen, okay? And then we will say that this one is oxygen. Okay, and if you look up here, these bonds, the distance between the nuclei of these, for oxygen, it's 66 pm, which stands for picometers, and for hydrogen, it's 30 pm. So that means oxygen is twice as long. The atomic radius is twice as long as it is for hydrogen, and we need to know why that is. Okay, so the distance between the nuclei are different for these elements. Hydrogen is the smallest, but iodine is the largest, as you see there. Okay, so let's talk about why. We call the distance between the two nuclei there the atomic radius. Okay, so you have the whole distance here, okay, and between half of it is the atomic radius. So you have the atomic radius of this part, and you have the atomic radius of that part. Okay, you could think of this as a kind of like circumference and radius in a circle. The radius is distance halfway between the edge of the circle and it's halfway between the full circle. It's from the middle to the edge of the circle. So um, that's what the atomic radius is for us. So it's one half the distance of the nuclei. We often measure the atomic radius in picometers, which is a very, very, very small number. That is 1 times 10 to the negative 12th meters. Okay. So another way of thinking about that is there are 1 trillion picometers in a meter. Okay. We've talked about nanometers so far. Talked about nanometers last unit. Nanometers are extremely, extremely small, but picometers are even smaller. There are 1 billion nanometers in 1 meter, but there are 1 trillion picometers in a meter. So these are sizes that we cannot visualize how small they are. Okay. So skip that one. So here is the trend in atomic size from top to bottom and left to right. So when you're talking about a periodic table, okay, so let me pull up my periodic table right here. When you're talking about a periodic table and you view it, you can either view it from left to right, right to left, top to bottom, or bottom to top. Whatever way you choose to view it, there's a trend for all of these. The first one is atomic radius right here. So atomic size increases from top to bottom. Okay. So what that means is as you go from here down to here, okay, and you stay in the same group, the atomic radius increases. Okay. You need to know that. You need to know as you go down, atomic radius increases. And as you go left to right, here it decreases. So you can see that. And decreases from left to right across a period. Periods run left to right. Okay. You need to make sure that you have that down. It's a very important trend to understand, and we'll talk about why in just a moment. Okay. So let's go back to this. So let's talk about why here. So as you go down, as the atomic, we're talking about top to bottom here because this is in terms of group. As the atomic number increases within a group, the charge on the nucleus increases and the number of occupied energy levels increases. So you have seen that when we've talked about, like, for instance, let me go back here and show you. Carbon right here, if you look at its electron configuration, which I need to click this. If you look at carbon's electron configuration here on the left for carbon, it ends in 2p2. Okay, silicon ends in 3p2. Germanium ends in 4p2. Tin is 5p2. Lead is 6p2, and then um, flerovium is 7p2. Okay, so as you go down, you add a shell there. That's what you're doing. You're adding an electron shell. And when you think about this logically, it's like you put it on a layer of clothing, right? If I am wearing, if it's cold outside and I'm wearing a jacket, I'm wearing, I guess, 2 layers, a shirt and a jacket. But if I put on like 5 more layers of clothing, well, I'm probably going to be more, warmer, but I'm also going to be wider. You can think of it that way. Okay? I'm definitely going to be wider. So the charge on the nucleus increases, and the number of occupied energy levels increases as you go down. Okay, so you are adding more protons there. So that is going to draw electrons closer to the nucleus, but that's not going to matter if you read this last bullet here as much as you add in more shells. Okay, the second bullet, or the bullet here, next one says the increase in the number of occupied orbitals shields electrons in the highest occupied energy level from the traction of protons in the nucleus. AKA, I mean, what that means is you're adding more electron shells, so you're making it harder to be attracted to the protons that are in the middle. Okay, you're farther away. Okay, just think about going to a basketball game. You're probably going to be more involved and enjoy the game better if you're on the front row rather than being at the very top. Okay, you're not going to be as interested. Okay? You're not going to be as attracted to it. That's a way that it may help you remember it. Okay, if you're going to go see somebody in concert, you'd much rather be in the front row rather than the back row. So And the last thing, I've already read this, but the chilling effect is greater than the effect of the increase in nuclear charge. Nuclear charge means the charge of the nucleus, which we know only contains protons and neutrons. Okay, so the atomic size increases. So if you go across the period, though, that's because that was from top to bottom. Across the period, though, the electrons are added to the same principal energy level. Maybe I'll turn the slide back on. Okay, so that was from top to bottom. So let me go back here and say this. So, for instance, if a question said, which has the larger radius, atomic radius, carbon or silicon, you would say it would be silicon because it is lower than carbon in the same group on the periodic table, so it has an extra electron shell, right? So when you answer questions with this stuff, you are going to have to explain why sometimes as well. But across the period, as you go left to right, the electrons are added to the same energy level. Okay, so as you go left to right, you are in the same shell. And when you stay in the same shell, the increasing nuclear charge pulls the electrons in the highest occupied energy level closer to the nucleus, and the atomic size is going to decrease. So essentially, you have the same shell, which is negative. The electron shells are negatively charged because they're electron shells, and electrons are negative. But you're adding more protons to the nucleus of an atom because as you go left to right, um, for instance, if you go from, if you look here and you go from aluminum has 13 protons, silicon has 14 protons, phosphorus 15, 16. As you go left to right, you add one proton. That's its atomic number. Okay. So whenever you do that, um, you keep the number of electron shells the same, but you're making the nucleus more positively charged. So it's bringing in the outer electrons, if that makes sense. So the atomic size is going to decrease as you go left to right. You are increasing the charge of the nucleus. So here's the trend for this. It generally decreases right to left, or left to right, sorry, and it increases top to bottom. Okay. I would remember it that way. I wouldn't remember it right to left or bottom to top, but you can do whatever you want. Okay. So that is the trend for atomic size. Okay. So that's the first part of this lesson. The next part talks about how do ions form. And this is going to be very important to understand because our next unit that we will cover deals with ionic compounds. Um, so it's important to know how ions form and what ions are. So we've talked about specifically only atoms this school year, but an ion is an atom or group or of atoms that has a positive or negative charge. Okay, simple definition: an ion is a charged particle. An atom is a neutral particle. Okay. So an atom is electronically neutral because it has equal numbers of protons and electrons. And we know that and we've used that. Right. But ions form when electrons are transferred. Okay, we do not transfer protons. If we were to transfer a proton, if that were to be possible, we would not have the same element because protons tell you what element you have. Okay, so when chemical bonding occurs, it is because of the transfer of electrons. So atoms of metals such as sodium, and this is important not just for this unit, but for the rest of the school year. Atoms of metals tend to form ions by losing one or more electrons in their highest occupied energy levels. So, what you need to know right now is that metals lose electrons and they become positive. Because if you're losing something that's negative, like if you lose you have a friend that's negative, you get rid of them, hopefully you become more positive. Okay. So, we call an ion with a positive charge a cation, not a cation, a cation. Okay. And I like to remember this because I love cats and cats have positive. Okay. That's a way to remember that. So, how you would write that is Na plus right there, as you see in yellow. Okay. That's how you would write a sodium cation. Right. So, opposite the metals, though, are nonmetals. Metals are on the left, nonmetals are on the right. Nonmetals like chlorine, bromine, iodine, fluorine, oxygen, you know, nitrogen, phosphorus, those things, tend to form ions by gaining one or more electrons. So metals lose electrons, nonmetals gain electrons. Okay, so make sure you know that. We call negatively charged ions anions. Okay, you can think of negative as antagonist, an right there, or some people like to say onion, but if you like onions, that wouldn't make sense. But antagonist, the evil person, negative. The charge for an anion is written as a number followed by a minus sign there. Okay, we're gonna skip that stuff. So we have cations and anions. Cations positive, anions negative. Cations belong to elements that are metals. Metals tend to form cations, and nonmetals tend to form anions. Okay, so that is the answer to that right there. Okay, so we're gonna stop there. Not too long of a video. Didn't want to cover the rest of the stuff because it would be really long. So we'll do that tomorrow. So watch this, answer the questions in the ed puzzle, fill out your notes, and everything will be good. Please let me know if you have questions about anything. We can schedule a Google Meet or do whatever. But I'm here to help you. So let me know if you need anything. Thank you. Hope you have a good day.